So you're going to use this website here. It's kind of a cool website. Let me walk you through it and show you what all it can do. So we've been working on Proton NMR. There is a thing called carbon NMR, although it's used less frequently, but it's still something that you will learn about if you take an organic chemistry class. It's still used quite a bit. But Proton NMR is the most common out of all of them. So if I just come down to Proton NMR and just pick the first one, like this. This is what's cool about it. So first off, it gives you the shift. Well, it gives you up here the formula right here like this. Boom, like so. And then it tells you the numbers that they're at over here on the left, the shift. And then it also tells you the area under the curve, which is the integration value. So basically it tells you everything you need to know to be able to solve the problem. And so I would recommend trying to solve it before you even go. One thing that I think would be helpful is if you looked at the range of where the proton peak values come in, like for instance, where does a carboxylic acid value come in, where does an aldehyde proton come in, so on and so forth, which I'm going to post in there with it. But anyways, this is very helpful. But then there is also this. If you scroll over this, it shows you that it's a singlet. And then if you scroll over this, it zooms in and shows a zoom in on what it actually is looking like. And then same with this. And then same with this. So therefore, we have nice little information. So then you should try to solve the problem like that. But after you get to that, I think what you should do is you can click solution. But I think you might learn a little bit more if you do this, continue. So if you can click continue, then we can just go through and answer these questions. So I'll just kind of work the first one with you. So it'll say, okay, how many different resonances are there? In other words, how many different chemical shifts are there? Well, there's 4 peaks. So therefore it's 4 and says you are right. So then if you click continue, then it says what type of proton is the peak at 3.77 parts per million. So if you can click here, hint, then 3.7 would be somewhere like right along in here. So therefore, let's see, maybe OH or a CHO, something like that. So there's 2 of those options. So let's just pick one. It says possibly. Let's just pick one of these. It says possibly. So it'll say it's either possibly one of those guys. Then it says what type of proton is present at 6.9. And so then again, you can pull that up. 6.9 would be right around in here. So, don't know. Oh, wait, there's the aromatic. So probably an aromatic compound. It says possibly. So then we go to the next one, 7.75, same thing. We go to 7.75 here. Oh, aromatic. So boom, click that. It says possibly, continue. 9.78, look at here. That's an aldehyde. That is definitely an aldehyde. So therefore we select this guy, continue. So now we've identified all the peaks and now it's showing us what it is. So we got an aldehyde, we got aromatics there, and then we got either the hydroxyl group or the ether group. So then it says, given the empirical formula, does a peak at 3.77 parts per million come from an hydroxide or from the hydrogen involved in an ether? Well, what it's asking about is this. Aromatics would suggest that it's like a benzene ring. So that's 6 carbons. Aldehyde would have another carbon, so 7. So we're missing a carbon. So therefore, this is going to have a carbon on it. So therefore, if I click this, it says yes, the aromatic contains 6 carbons and the aldehyde 1. Since the empirical formula indicates the presence of 8 carbons, the proton resonating 3.77 must be attached to a carbon. So therefore, now we have every information that we need to know, except one tiny little bit. What is the substitution pattern on the benzene ring? What does that mean? Mono, ortho, metapara? Well, it says hint. Basically, it's saying, okay, where is the positioning of these groups. So we know we have an aldehyde attached to the benzene ring, but we also will have an ether, like an OCH3, attached to it as well. So the question is, where is it? In other words, it can't be this one, because this one is only just one substituent on the benzene ring. The ortho would be where this is like the aldehyde and this would be the ether group. The problem with this is, though, that each one of these hydrogens would not be chemically equivalent because their spacing around them are different. Same thing with meta. This one would be different, this one would be different, this one would be different, this one would be different. Because of their relative distances to both the ether and the aldehyde group. But the para position would give, there's one for the aldehyde, and there's one for the ether hydrogen, and then these guys would be chemically equivalent. So that's 3, and these guys would be chemically equivalent. So therefore, there should be 4. So therefore, it's going to be in the para position. And then it talks about basically what I just said. And then I click continue, and then I got it. And so this is the structure, just like that. And it says, given the empirical formula on the right and the structure shown on the right, how many protons must be present on the OCH? Well, we know that. It's got to be 3. So it's pretty simple. And then check the J splittings. We already talked about that. It is consistent, yes. And it talks about why it's consistent. The integral values, you can check those. Yes, they are consistent, and then we are ready and done with that problem. So here's what I'd recommend doing. I don't think, I know that's kind of a lot of questions. Basically, it's asking you step by step, okay, what does this mean? What does this mean? What does this mean? What does this mean about the structure? So on and so forth. What I would try to do is I'd try to solve them on their own. And then if you don't get it correct, and then check the solution. If you don't get it correct, then I'd like for you to go through that kind of step process that I just talked to you about. And I think that should help.